Okay, good. All right, so we have been studying circles, and there's so many concepts that we've been doing that I figured it'd be really good to start this video off with just all the concepts, just all the main ones. I mean, I think you guys already know how many degrees are in a circle all the way around? 360. It's the same reason that like when you jump and do a full spin, they call it a 360, right? If you didn't know that, have your mind blown. That's why. All right. Yeah.
Are you doing something like that?
Yes.
Is there anything I say?
Yeah. Yes. Gilbert, you're on the tape now. Sorry. All right. So right here, guys, quick idea. I'm not going to work all these problems out. How would I find the distance of, let's say, the radius in this problem? Yeah, you do a squared plus b squared equals c squared. But wait, the Pythagorean theorem only works on 90-degree triangles. So how do you know that this is a 90-degree triangle? Any ideas?
Because the triangle is going through the diameter.
Yeah, because the triangle is going through the diameter. This is the diameter, and we do know that because it's a chord that's passing through the center point. So that's a diameter, right? Which means that this angle right here is 180 degrees, right? That arc length is 180 degrees, and because this is the triangle, or the two chords that are making that, so because this is going out to that point and the other end of the diameter, that means this angle should be half, because on the edge, right? It's not in the middle, it's on the edge. Should be half of that 180 degrees. So that's a 90-degree angle. So yeah, if we wanted to find out what the radius here would be, we would just do a squared, so maybe 8 squared plus b squared, so maybe 12 squared, equals the diameter, c squared, okay? And then we'd end up taking the square root of this and the square root of that, so you'd have c equals that. And you'd get the length of the diameter, then you could just divide it by 2 if you wanted the radius. Just going over that. I'm going to recap everything real quick, okay? So that's one concept that you can't forget. If I wanted to find the diameter here, how would I do that?
It's like 90, 180, like something angle. I don't know. I never understood that.
This is the same concept. Same concept.
What did you ask?
How would I find the diameter here? But you have to have the foresight of seeing that the diameter is just this. Right? So it'd be a squared plus b squared equals c squared. That is what you said?
Yeah, so point down.
Okay. Well, what you gotta provide more than that. More than just one point to the other point. Okay. So yes, then you can do a squared plus b squared equals this distance squared. Okay. What? That? Does it look like a butt?
No.
That's on film. Come on, Claire. Mature. Grow up. Please. Please. All right. What do you know about these two chords from TV? What do you chord TV. Ooh. There, it equals RS. It does equal RS. How do you know that? What line? Yeah. This arc we know is the same as that arc. And if that chord makes this arc and this chord makes a congruent arc, then the chords have to be congruent. Okay.
Hi. Do you know Angela Vanera?
Yes.
That's for sixth grade.
Thank you. So those chords are congruent. So if I'm going to solve for x here, all I'd have to do is say 5x minus 9 has to equal 2x plus 3, and then I can solve from here. So I could subtract. So I got 3x equals, add the 9, 12, x equals 4. And I skip steps there. If you want to pause it and figure out how to do it on the video or whatever, that's fine. The point is, this equals that because these two arcs are the same, and those are the chords that make those arcs. All right? So y'all remember that? Most of the stuff is pretty straightforward. Most of the stuff you'd probably guess, but there's theorems that make all this stuff true. All right, so if I were to ask you what's the distance from P to T on this, what would you be able to tell me? It's 6, and and again, that just kind of demonstrates what I was saying. You would guess that it's 6, right? Just by looking at it. But how do you know that it's 6? Well, so honestly, you guys said quite a few things, so I'm just going to tell you the answer. I don't know who said the right answer and who didn't, and that's fine. So remember, though, there's a theorem that if you have a chord that is perpendicular to a radius or a diameter or something like that, if it's perpendicular, then that radius or that diameter bisects that chord. Remember that? So that means this has to be the same as this if it's perpendicular. Right? And so because it's perpendicular, then we know it bisects. So if that's 6, then that has to be 6. Okay, we're good there? Just quick review. All right. What are they getting at on this one? That they're equal. So you have two angles being compared. You have an angle that's measured 3x minus 5, and you have another angle measure of 2x plus 15. Now I heard that they're equal. How would you rationalize that based on this picture? Yeah, they both open up to SV. They both open up, both of them are creating the exact same size arc, right? And because they're both located on the outside, that means both of them are half of that arc's measure. Whatever the arc is, say it's 100, that means both of them are 50, right? Say it's 200, then both of them are 100, right? So they're both the same. We might not know what the arc is, or the arc measurement, right? But we know that they're the same because they both are opening up to that exact arc. Does that make sense? So again, it's just more so being logical than anything else. So if we know they're the same, you can set them equal to each other, and you can solve that. So I'm going to subtract the 2x, x equals, I'm going to add the 5, 20. Okay? And that would be it. X equals 20, and then I could answer whatever questions they would ask me in that situation. This one. What if I asked you, what's the distance in degrees of arc CF? What's the measure in degrees of arc CF? 90?
Yeah. 80.
80. How do you get 80? It's twice that 40, right? The 40-degree angle is making it. And the 40-degree angle is on the outside, right? If it were dead center, right? Which dead center is probably right about there than here, rather than there. If you're dead center, and then this were a 40-degree angle there, what would be the distance of this? That'd be 40, right? If it's dead center, then the arc length is the exact same. If it's on the outside, then the arc length is half of it. All right? And pretty much, I think that's all the information that we would need. I mean, and so if that's 40, then what's C? What's the measure of C?
49.
Well, it's creating this, isn't it? So it's half of that. If you can do half of it in your head, great. If you can't, you understand at least that C, angle C, is creating this arc on the outside, right? Of 48 or of 98 degrees. So that would have to be 49 degrees to create that. It's half of it. All right. So just doing some review there. Good. Okay. So now we're going to be doing.
I have a question.
Huh.
What about the one that you said was like a quadrilateral or something? The one that made like 180 or something? Like a circle?
Maybe I have. I remember though. I did have one that I wanted to talk about. Ooh, that's algebra 2. Okay, look at that. In a circle. So like, are you talking maybe something like? Oh yeah, there was something like this. And you have a quadrilateral inscribed in a circle, right?
And it's opposites or like.
I think you were laughing because it's not like perfectly made. I didn't want it to be perfect. This and this are supplementary. They add up to 180. Remember that? And this, shoot, I messed up. I should not have put that the same degree, right? They just add up to 180. They're not the same. They're not necessarily the same measure, okay? But they do add up to 180. So if this is angle A and this is angle B, then A plus B equals 180 degrees. Okay? We got that? Is that what you were asking?
Yeah.
Yep. I'm glad you asked that. Oh, yeah. And let's go back. Which is inscribed and which one's circumscribed?
Inscribed is the quadrilateral.
Yep. And circumscribed is the circle, right? Now, if I put a quadrilateral out here, Oops. Yeah. And the quadrilateral is the circumscribed one. So that would be a circumscribed quadrilateral. Inscribed in it would be the circle, right? Okay, cool. Great. So y'all hopefully are already open to this page. Just a few things I need to explain. Should be pretty easy. I'm going to go straight out of the book. See if... Okay, that should be good right there. All right, so, yes. Okay, I think I got one sitting right here. All right, so have you ever heard somebody say that they went on a tangent? They just went on a tangent.
Yeah.
So when somebody says, and this is a really good word to add to your vocabulary. I'm not even kidding. When somebody goes onto a tangent, they're not talking about a circle necessarily. The definition of a tangent, so for example, in calculus, when you guys get to calculus, you'll be doing tangents of curves. So like if that's a curve, you might have a tangent line right here. Now what a tangent line is a line that only touches that curve in one spot. It touches in one spot. Does that make sense? So if I am having a conversation with somebody and I'm talking about math, right? And I'm saying, man, math, I love the subjects of math. It's great. And somebody will be like, speaking of math, I have English next period. And they kind of like take the whole conversation, they go in a different direction. And the only tangent point, the only point that touches the previous conversation that I was just talking about, was somehow they linked that English to that math. Does that make sense? It barely even is on topic. Does that make sense? So when somebody says, that was a complete tangent, that's actually what they're referencing. They're saying, what you just said only touched what my conversation, what I was talking about, only in one area. Like it hardly even related. Does that make sense?
Yes.
So, for example, when I'm having a conversation, or when you're having a conversation today and somebody butts in and changes subjects, right? And it hardly even links to what you were just saying, you can be like, you just went on a complete tangent.
And then walk away.
Yeah, and then just be like, stupid. But no, that's what a tangent is. So when you hear that, this is what they're referencing. So when you have a tangent line, right, it's touching that circle in how many spots? One spot, by the definition of what it means to be tangent. And that one spot would be the point of tangency. So a common tangent, that's when you're talking multiple circles. So they have a common tangent if you can draw a line through them that hits each of those circles in only one spot, right? So this one has a common tangent right here. It actually has more than one common tangent. Can you see? There's two more that I can see. Yeah. So here would be a common tangent. If I can draw it perfectly, like that, right? And it hits one spot, or other way. And it hits one spot. Those are two more tangents, right? And they're common tangents because they run tangent to both circles. Honestly, I don't know if we're even going to talk about this concept of common tangency. I don't think it's a big topic. So when you look at this, can you see a common tangent? Right here, right? One. This one, can you see a common tangent?
Oh, yeah.
Actually, there's quite a few here. Oh, you can see them. I already drew them out here. 1, 2, inside, right? So that one's got 4 common tangents. So just so you are familiar with common tangents, how many does this one have?
1.
On the side.
Yeah, just this one right here. That would be the only common tangent they would have. All right. Going on to the next page. So I'm guessing we're going to get into some theorems here. Now, most of this stuff makes sense. All right, here's a cool one. So I'm gonna show you what it's talking about. Does anybody mind being recorded? Does anybody not care if they're recorded? Okay. Do you want to come? So come up here. Make any tangent on here, on this circle.
Anywhere?
Yeah. Any tangent on the circle, touching the circle in one spot. Okay. Now, what is the relationship between the point where this tangent touches that circle right there and its radius? What do you think? If you can't see it, why don't you go ahead and make another one? Go ahead, make it any tangent anywhere. We'll cheat it. We'll cheat it. Okay. So look, there's the point of tangency right there. So what's the relationship between that radius and that tangent line, and this radius and that tangent line? They're perpendicular. They're perpendicular. And any tangent line, so for example, if I draw, see, I have a tough time with it too. If I draw right there, right, the radius is perpendicular to the tangent line, always. Okay? So, thanks, that's perfect. I was just going to use you as an example to put any kind of tangent line up there. And any radius that draws to that point of tangency is going to be perpendicular. Okay, so with that being said, let's look back at this book, and that's what this is saying. In a plane, a line is tangent to a circle if and only if it is perpendicular to a radius drawn to the point of tangency. So it's saying, pretty much, you know that this is a tangent or it hits in one spot if that's perpendicular and it's hitting the point of tangency. So pretty much you're just looking for it. Make sure that's a 90-degree angle before you assume that it's actually a tangent. All right? But with that being said, let's see how it applies now. This is going to get rough. Okay. So it says determine whether KL, determine whether this, oh, KL, sorry. My bad. All right, determine whether KL is a tangent line or not, right? And a tangent line would only hit in one spot. If it were a tangent line, what are you trying to prove? That they're perpendicular, that it's 90 degrees. And if they were, then you know that a squared plus b squared would equal, ooh, this is tricky. It's saying that this is 9. And if that's 9, what is this part? It's 8. If that's the radius there, and that's 8, then that's 8, right? So equals 17 squared. So that's the question. If that's true, then it is a tangent, right? It is 90 degrees. If it's not, then it's not a tangent. You guys good with that? Yeah. That's the concept there. So, one more time. If you're going to prove that this is a tangent, then what you're looking for is to prove that 8 squared plus 6 squared equals, I don't like how they do this, honestly. I think they're saying that that's supposed to be 12 and that this is supposed to be 6. Or they might be saying, more realistic looking to me, is that the whole thing would be 12. It's just kind of, it's very kind of broad and not specific there. But I think you get the point, right? You're trying to prove that this squared plus this squared equals that squared. And if it does, then that is a 90-degree angle. Okay, and it's tangent. All right, everybody good with that? All right, let's keep going with this. I just want to get all of these examples out of the way, and then you guys can start practicing. Okay, that's just the same idea, except a tougher sort of problem. Same idea. So, going to the next page. All right, this is probably a new theorem. Oh, this is, so we're not going to practice constructions. Oops. Okay, here's another one. I'm just going to make some stuff up. But here's a point. Now, if I drew the tangent line from that point, let's see if I can do it. From this point to here, tangent. From this point to where it runs tangent right there. What do you think the relationship between these two lines are going to be? Same lengths. Yep, they're going to be congruent. Does that make sense? And you guys can see that. It doesn't matter what point I make. Look, let me try to exaggerate this a little bit. Let me take all this and let me scale it down. I'm going to just make this a lot bigger of an example. So even if I had that, right? And I take a point randomly, let's just keep using the same point. It's still going to be the same size. So this up to here, and then this to here. Do you see why those would be the same length? Okay? Because from here to here, right? Be one length, and then they both go out the same amount. So they're growing by the same amount, right? To reach those outside points. So it makes complete sense. Okay. Any questions on that concept? So that's what they're trying to get across right here. So if you have two segments from the same exterior point are tangent to a circle, then they are congruent. Then those segments, B to A and B to C, are going to be congruent. So right here, it's saying, all right, here's a point B, and it runs tangent to point A, and B to C runs tangent also. So that means those have to be equal to each other. And that's what you see them doing right here when they set it up. They just make them equal to each other. Are we good with that? All right. Still got a good bit of time. So same thing here. So not going to worry about that right now. And all right, what you guys are going to do now, finally, and if you don't finish, then you can take pictures and try to do it for homework. What is this? Hopefully we're done. I think we're done. Yeah. Okay, so do number 2, 3. I'll give you guys a deal. Do all the evens through 16 at least. So that should be only 8 problems. Yeah, through 22. So do all the evens all the way through 22. And that'll work.